minimizers of anisotropic attractive-repulsive interaction energies. So yeah, thank you.
Thanks for the introduction and thanks for the invitation. It is really my great pleasure to speak here. So today I'm going to talk about my joint work with Jose Carrillo on the energy minimizers of some anisotropic attractive-repulsive interaction energies. And I will focus on the case of two spatial dimensions. Let me start by introducing the model and also say a little bit about previous results on this model. So this interaction energy model originates from the study of dislocations in crystals, which is part of the material science. So if you imagine a perfect crystal, it has a periodic structure. But in reality, sometimes crystals are not so perfect. There are some kind of like extra atoms inserted into those crystals, like this one. So this will cause the shape of this crystal structure to distort a little bit. And this phenomena is called dislocation. And you can see that there can be very different situations of dislocations. For example, you can insert a whole layer of atoms into your crystal and then push all the other atoms a little bit far away. And this is called an edge dislocation. And another possible situation is a so-called screw dislocation, where you just put one extra line of atoms into your crystal, and then around this line, the original lattice structure kind of screw around this line. So then our question is how to model these dislocations in the crystals. In the literature, people have developed some phenomenological models to describe those dislocations. And in those models, each dislocation can be described just as one particle in space. For example, if you take an edge dislocation, you can just model this dislocation by exactly the location of this atom. And you can view that as living in the two-dimensional space, which is parallel to the screen, because you have a whole layer of dislocation atoms. And so in this case, an edge dislocation can be viewed as a particle in 2D. And similarly, if you take a screw dislocation, it can be viewed as a particle in 3D. Okay, so the problem is about doing this kind of particle model is that the number of dislocations in a crystal can be huge. For example, a typical scaling of the number of dislocations can be like 10 to the 15 per square meter in the case of the edge dislocation. So in reality, if you use a particle model, then it is not very effective. And of course, a more effective way is to use a continuum model to describe the spatial dislocation of dislocations. Let's say we just use some density function to describe this spatial configuration. So this is the model we are going to focus on. So we take rho as a density function for the dislocations, which is in general a probability measure on R2. And then those dislocations have pairwise interaction energy, and this interaction is described by some pairwise interaction potential W. So if you compare this model with typical pairwise interaction model in collective dynamics, the major difference is that here it's very natural to have an anisotropic interaction potential, which means that along different directions, the interaction energy behaves differently. This is very natural in the situation for dislocations because for a single dislocation, it has an orientation, and it is clear that if you have two dislocations, their interaction behaves very differently if they are along this vertical direction or perpendicular to the vertical direction. Okay, so this anisotropic property of the interaction potential means that your W is not merely a function of the modulus of X. It also involves some dependence on the angular variable, which is denoted as theta in the two-dimensional setting. Okay, so we will focus on just one special class of interaction potentials. The major part of this is anisotropic repulsion, which has a singular part x modulus to the minus s and multiplied by another part omega of theta, which describes the anisotropy of your interaction potential. And also, typically, if you want to minimize the energy and don't want everything to go to infinity, people consider a situation where you have some confining potential. And in the case of quadratic confining potential, which is maybe the simplest case, it is also equivalent to a quadratic pairwise interaction. So for the sake of notational simplicity, we write it in the form of a quadratic pairwise interaction. So this is our attractive repulsive interaction energy, which is anisotropic. So here we will consider the case when the singularity index S to be between 0 and 2. And then another important case is a logarithmic case, which approximately just corresponds to the case S equals 0 in this. So in fact, this kind of logarithmic potential can be derived as the limit S goes to 0 for this kind of Riesz-type interaction energy. Okay, so there have been some previous results on the logarithmic anisotropic interaction energy. And what people have already considered is like just one particular case for the anisotropic part. That is, when your anisotropic part, like the capital omega of theta, behaves like some constant times the little omega theta. By the way, this is also a very common way of studying the phase transitions in this kind of energy minimizers. You just try to build a class of interaction energy by inserting some parameter like this alpha here. This alpha actually describes the strength of the anisotropy. So see, suppose alpha is equal to 0, then you have just an isotropic potential. And this is already very well studied. And as you make your alpha larger and larger, then the anisotropic effect becomes stronger and stronger. And you can try to observe like how the energy minimizer changes as the anisotropy becomes stronger and stronger. So here, what people have studied is just one particular profile for the anisotropic part, which is cosine square of theta. You can see that for theta equals 0, which is the horizontal direction here, for that, the little omega is equal to 1, which is the largest value. So this horizontal direction is not preferred. On the other hand, if you look at the vertical direction, theta equals pi over 2, then the omega of theta is minimized, which gives the value of 0. So the vertical direction is preferred for this anisotropic interaction potential. Okay, so for the isotropic part, alpha equals 0. This is a classical result, goes back to Frostman in 1935. Who showed that the unique energy minimizer is a characteristic function of a ball. And about anisotropic cases, the first result was given by Mora, Rondi, and Scardiel in 2019, which deals with the case alpha equals 1, just one particular case. In this case, they showed that the unique energy minimizer is given by a one-dimensional vertical distribution. You see that the vertical direction is indeed preferred. And later on, a work by Carrillo, Matteau, Mora, Rondi, Scardia, and Verdera in 2020 filled in the other values of parameter alpha in this model. So first, they showed that when your alpha is between 0 and 1, there is actually a continuum transition from the characteristic function of a ball to a one-dimensional vertical distribution. And actually, they showed that the minimizers for alpha values here are all given by characteristic functions of some ellipse, and the size of the ellipse can be determined explicitly. And they also show that if you take alpha larger than 1, then the vertical 1D distribution is always the minimizer. Okay, and there have been some extension of this kind of results. For example, just for example, in the three-dimensional case, the same group of people in 2021 gives a result on just one particular angular distribution, and they also obtained ellipse-shaped minimizers. And also a work by Matteau, Mora, Rondi, Scardia, and Verdera in 2021 deals with the case when you start from just this logarithmic plus quadratic, but add some perturbation term which can be general. And in this case, they also showed that the minimizers have to be ellipses. Okay, so of course, now we can ask the question, this problem up to now, it is not very well understood. For example, we said that we can discuss about more general Riesz-type singularity here. So basically, previous results only understand like the case S equals 0, but what about for general S? Do you still expect this kind of nice behavior? And also, what about general omega? So here we have the result for general omega if the magnitude of anisotropy is small, but what if it is large? So the main questions are like, do we still have those kind of ellipse-shaped minimizers? And also, do we still have the collapse to lower dimension for the minimizers? Okay, so to give you some ideas about what's going on, let me show you a very surprising numerical simulation result in a very generic situation. So here, what I take is just this kind of anisotropic interaction potential with a parameter alpha as the strength of the anisotropy. And here we take the Riesz-type repulsion with S equals 0.4, and our angular profile is like a linear combination of cosine to the fourth and cosine squared. So this little omega still prefers the vertical direction. So somehow I expect that your minimizers will be elongated along the vertical direction. So let's see what's going on here. For this kind of Riesz-type repulsive interaction with quadratic attraction, if you have the isotropic part, isotropic case, alpha equals 0, it is known that the minimizer has to be radially symmetric, which is this case. And as you make alpha larger and larger, you can observe that when alpha is not too large, you still have the ellipse-shaped minimizer. And there is just one critical value, which I would call alpha L, such that once your alpha passes this value, then suddenly the minimizer breaks into pieces. It collapses into some kind of lower dimensional size. And later on, I will tell you that this actually corresponds to a threshold value for a convexity condition called the linear interpolation convexity. Okay, so once we pass that, you see that if you further increase the alpha, you have some very complicated behavior. And of course, if the anisotropy is stronger and stronger, you expect that everything is compressed into the vertical distribution. And here, the magic thing is that there is still one particular value, which I will call alpha star, such that once you pass this value, the minimizer collapses exactly into a one-dimensional vertical distribution without any error there. So it's not very trivial why after such a complicated phase, you can still recover this one-dimensional vertical movement. Okay, so in this talk, I will tell you like every detail about this thing. Okay, so first of all, as some preparation, I will discuss the linear interpolation convexity property, which is a key property to this kind of interaction energy problems, and how this is related to the Fourier transform. Then I will discuss the different cases according to the size of the alpha. Okay, so the linear interpolation convexity is actually quite a classical idea. So we say that some energy functional E, or we can say that for some interaction potential W, has a linear interpolation convexity property if we have the following property. For any complexly supported measures, rho 0 and rho 1, with the same mass and center of mass, the function, if we define a function which maps T to the energy of a linear interpolation between rho 0 and rho 1, this function of T is always strictly convex. So this property is important because it automatically implies the uniqueness of energy minimizer up to translation. So the reason is very simple. Suppose I have two different energy minimizers. They have to have the same amount of energy. Then, if you are discussing up to translation, you can always assume that they have the same center of mass. Then just do a linear interpolation. And if you have two different measures like that, this linear interpolation tells you that the energy in between is strictly convex. So for the value T equals 1/2, you get some probability measure with a smaller energy, which contradicts your assumption that you are taking minimizers, right? So this implies the uniqueness of minimizers. And to understand this condition better, you can say that for this function of T, to check the convexity, you take the second order derivative. What you actually get is just E of rho 1 minus rho 0. Rho 1 minus rho 0 is just some signed measure with some vanishing moments. So basically, this condition is equivalent to say that if you take the energy and apply it on some signed measure with vanishing zeros and first moments corresponding to mass and center of mass, then it is always positive. Okay, so to check this condition, it's better to rewrite the total energy into a different form by using the Fourier transform. Because here, it is actually the inner product of W convolved rho with rho. So you use factorial to go to the Fourier side, and convolution becomes product. At least formally speaking, it becomes the integral of W hat rho hat squared. Of course, if your W has some growth at infinity, you have to deal with some possible singularity of W near 0, but typically it is a minor issue. So we can say that if you want this to be positive for any signed measure mu inserted into here, then you are basically requiring that W hat is non-negative. Okay, so this linear interpolation convexity has been classically used for many different types of energy minimization problems. And about interaction energy, I think it gains popularity in both isotropic and anisotropic in the recent years. Okay, so about this energy functional, if you care about the energy minimizers, a very natural thing to do is to derive the Euler-Lagrange condition for energy minimizer. And this was done in the work of Carrillo, Laurent, and Rao in 2013, which basically says that the generated potential W convolved rho has to achieve minimum on the support of rho. So basically, you can say that W convolved rho is some constant value on the support of rho and larger outside. So that's the Euler-Lagrange condition for the energy minimizer, which is a necessary condition. And the important thing about potentials with linear interpolation convexity is that this Euler-Lagrange condition is also sufficient in this case. That is to say that the unique energy minimizer is the only probability measure satisfying this condition in the case of LIC. Okay, so this was observed for this kind of anisotropic potential in this work by Carrillo and co-authors, and also a work of Carrillo and myself used a similar thing in the context of isotropic potentials. And actually, the ellipse-shaped minimizers in the previous work are proved just by verifying the Euler-Lagrange condition for the ellipse-shaped minimizers. Because once you verified that, once you have the LIC property, and also you verified that some rho satisfies this Euler-Lagrange condition, then you can directly say that this rho is the unique energy minimizer. Okay, so this motivates us to study the Fourier transform of the anisotropic potential, because if we are in a case of LIC, then everything is a lot simplified. For example, we have uniqueness of energy minimizer, and we can check that just by using the Euler-Lagrange condition. Okay, so what we did is to take the Fourier transform of the anisotropic potential of the form x to the minus s times omega of theta. That's kind of a very typical form of anisotropic potentials. And it turns out that by some very explicit calculation, we can get this formula. It is still of a very similar form on the Fourier side. And here the angle function, which I denoted the angle variable on the Fourier side by phi, is given by some convolution operator acting on omega, at least for a particular range of x. Okay, and of course, since the Fourier transform and the inverse Fourier transform are basically the same, you can also apply the same formula reversely to express your omega in terms of omega tilde, which is a Fourier side angle function, by using a similar kind of convolution operator.
So you're taking Fourier transform on both x and theta.
So theta is the angle variable of x. So I'm taking a two-dimensional Fourier transform. Okay, so using this very explicit formula for the Fourier transform, we can get the equivalence between the positivity of the Fourier transform and the LIC property in a very precise way. Actually, what we proved here is that this kind of anisotropic interaction potential has the LIC property if and only if the Fourier transform is non-negative. Okay, so this looks a little bit weird because the LIC property is supposed to be a strict convexity property, a strict inequality, but it is equivalent to some non-strict inequality. So actually, this issue comes from some argument by using complex analysis, because in the LIC property, we always deal with complexly supported probability measures. And if you take the Fourier transform of that, you get some function which is actually a holomorphic function in the perceived variable. So this is actually how we get this strict inequality equivalent to non-strict inequality. Okay, so this is very nice because using the explicit formula for the Fourier transform, we know exactly what are the situations where we have the LIC property for the anisotropic potentials. And also, we can get more information if in the case of LIC fails. Actually, what we can prove is that if LIC fails, then W immediately start to have the so-called infinitesimally concave property, which was a concept we proposed in an earlier work. So this property basically tells you that the minimizers get unstable on any small scale. If you have a little bulk in your minimizer, then it is actually in your probability measure, then it is actually unstable with respect to energy. If you break into pieces, the energy gets smaller. So that basically tells you that for any energy minimizer, it cannot contain any bulk like that. So this is basically suggesting that the energy minimizer has to collapse into lower dimensions. So basically the information here is that either you are in a nice situation where you have uniqueness of energy minimizer, or it has to collapse into lower dimensions. If you look at some potentials like that with a parameter alpha and angular profile little omega, then we can separate into two different cases. If S is between 0 and 1, then we can show that the Fourier transform of the little omega part is always sign changing. So if you look at the Fourier transform, take alpha sufficiently large, then the Fourier transform becomes negative somewhere. And in this case, there is a threshold value alpha L such that before that, you always have the LIC property, energy minimizer is unique. After that, it becomes non-LIC, and basically minimizer has to collapse into lower dimensions. And the case of S between 1 and 2 is somehow boring because we can show that the LIC property always holds in this case. So you always have a unique minimizer. So since it is boring, I will focus on the case S between 0 and 1 in the rest of the talk. Okay, so we first deal with the LIC case, and we will show that the minimizers, we know it's unique. It always has a shape of some ellipse. So we first formulate the candidates of the minimizers. So of course, the original isotropic minimizer, that's one candidate at least for alpha equals 0. So for the case of the isotropic interaction energy, it was known that the unique energy minimizer has this very explicit formula, which is supported on some ball of radius, I call it R2, which depends on the singularity index S. Okay, so the natural candidates to form the ellipse-shaped minimizer is to do some rescaled and rotated version of this radially symmetric shape. So we just rescale it in the x1 and x2 axis by some positive numbers A and B so that it becomes ellipse-shaped, and we also rotate by some angle eta. So generally speaking, we have some candidate of the minimizers of this shape. And we also allow this kind of thing to be degenerated, that is, taking the limit like A goes to 0 or B goes to 0. In that case, we get some one-dimensional distribution, which can be viewed as a weak limit of those ellipse-shaped distributions. Okay, so here is our theorem about the ellipse-shaped minimizers. Suppose we have S between 0 and 1 and consider this anisotropic interaction energy, then suppose we have some more strict version of our LIC, saying that the Fourier transform is strictly bounded from below in the angle variable, that is omega tilde. Then we get to the conclusion that the unique energy minimizer has to be some non-degenerate ellipse-shaped distribution as in the previous slide. And suppose you just assume the LIC equivalent to omega tilde non-negative, then there is some possibly degenerate ellipse-shaped distribution, which is a unique minimizer. Okay, so the strength of our results compared to previous results is that we can deal with like a very general angular profile omega, and it covers all of the LIC cases. So in other words, suppose we consider the anisotropic potential parameterized by alpha. Then starting from alpha equals 0, we know that as long as we are in the LRC case, we always have this kind of ellipse-shaped minimizer. And once we pass alpha L, the minimizer cannot be ellipse-shaped because we said that in this non-LRC cases, we cannot have any bulk in your minimizer. Okay, so this means that we have obtained all the possible ellipse-shaped minimizers on the spectrum of alpha. Okay, so the proof of this result is basically still you take that ellipse-shaped distribution and check the Euler-Lagrange condition, and then by the LRC property, if the Euler-Lagrange condition is true, then it has to be the unique minimizer. That means we have to calculate the potential generated by this ellipse-shaped distribution very carefully. So our key lemma is like the following. Suppose you take this anisotropic potential x to the minus s times omega of theta, if you pair with some very particular quadratic potential, and then take the generated potential for the ellipse-shaped distribution, then it satisfies the Euler-Lagrange condition. That is, it is equal to a constant inside the support. And if you are in the case of LRC, we can also show that it is larger outside the support. And here, how much quadratic potential you need in this result is completely determined by those formula, which involves the Fourier transform of the anisotropic potential. And that's exactly why we can get a complete result for those ellipses, because here we already use the information from the Fourier transform, and it can be directly connected to the LRC condition omega tilde being non-negative. Okay, so from this lemma, it's very easy to obtain the final result for the ellipses, because you just need to find the correct parameters little a, little b, and also the rotation angle eta to make the quadratic the one you want. You try to solve the equation capital A, capital B equals 1, capital D equals 0 with 3 unknowns. And just by a little bit effort, you can show that there always exists a solution, which gives you the meaning. Okay, so the proof of this lemma is based on interesting observation that for any anisotropic potential of the form x to the minus s times omega of theta, you can actually decompose it into a linear combination of one-dimensional potentials. So basically the idea is that starting from the formula for the Fourier transform, we see that it has a convolutional structure. I mean the formula from omega tilde, the Fourier side to the physical side. On this formula, if you multiply it by x to the minus s, on the left-hand side, you recover the anisotropic potential. On the right-hand side, if you combine the x to the minus s with this term, you get x dot with a unit vector in the direction of phi to the minus s. And this is exactly a one-dimensional potential along the direction of phi. So if you want to compute the convolution of this with rho AB, then you only need to do the convolution of this with rho AB and then assemble everything together. Okay, so this convolution is basically some one-dimensional thing. If you look at the picture here, only the E phi direction matters. The E phi curve direction doesn't matter at all. So you can just integrate your rho AB along the E phi curve direction. That is, you are doing the push forward by some projection operator onto the E phi direction. And the magic here is that if you take this push forward of rho AB onto some one-dimensional set, some one-dimensional line, then it becomes exactly a one-dimensional energy minimizer for one-dimensional interaction potential. And the power stays the same here. So that means if you view everything just in the direction of E phi, if you pair this x to the basically little x to the minus s with some proper quadratic potential in the same direction, then you get exactly what happens for energy minimizer. That is constant in between and larger outside. Okay, so in notations, it is like the following. If you pair this one-dimensional singular potential with some proper amount of quadratic potential, then it is just the generate potential is just something in the E5 direction, and it is equal to some constant inside the support and greater than this constant outside. Okay, that means for the generated potential just along the phi direction, it is constant in this whole band and larger outside. So in particular, you see this generated potential is constant in row AB, in support of row AB. Right? So if you do that along different directions, you always get some constant inside your row AB. So if you assemble everything together by integrating in phi with the wave function as a Fourier transform, then you still get this generated potential is constant inside. And why in the case omega non-negative, it is greater outside? Because originally it is all greater outside. If you do some positive linear combination, you still have something greater outside. Okay, so that is the proof of the lemma and finish the case of all the ellipses. And what about the collapse into one spatial dimensions? So our result is like, suppose you take some anisotropic potential with parameter alpha, which favors the vertical direction. As long as your omega is somehow non-degenerate near this vertical direction, that is, it is bounded from below by a quadratic function. Then you basically imagine having enough coercivity to push it into the one-dimension distribution. Then we can prove that for sufficiently large alpha, the minimizer has to collapse to a one-dimensional vertical distribution, which is some kind of one-dimensional minimizer. Okay, so now we have this picture like for small alpha, you have LIC and the minimizers are ellipses, and for large enough alpha, you just have the one-dimensional minimizer. This basically recovers all the situations in the previous cases. And of course, there can be a gap in between. And we saw in the previous macro simulation that there is indeed a gap. By the way, let me also mention that this non-degeneracy condition is indeed necessary, because if it fails, we have examples that it never collapses exactly into vertical. Okay, so the proof of this is actually quite short. Basically, we just try to use the same kind of comparison argument in the previous work by Carrillo and co-authors. Basically, it says that suppose you are in a nice situation where there is no gap in between. You start from the ellipses and you get into the critical value of LIC. Suppose you collapse exactly into one dimension. Then this one dimension has to propagate for all larger alpha just by a very simple comparison argument. So for general little omega, this collapse might not be true at exactly alpha L, but we can compare with some other profile such that this is true. So the main point is that as long as for general similarity S, we can construct such a profile omega star to compare with, then the whole comparison argument becomes straightforward. And this construction of the very particular omega star such that there is no gap is just based on all the theory of the ellipses, where try to find the omega star such that the ellipses exactly collapse into 1D at the critical alpha. Okay, so finally, what happens in between? I mean, in here. So although here the phenomena becomes very complicated and we cannot get a very detailed description of the minimizers, we can indeed get some information. For example, we can guarantee that for some situations, vertical segments cannot appear, so that you have to have zigzags. To do that, you just try to say that if you take some vertical segment like that, and you try to compute the local expansion of the generated potential near this vertical segment. Suppose the generated potential goes down near this one-dimensional distribution, then it cannot serve as a minimizer because it violates the Euler-Lagrange condition. Okay, and it turns out that the leading term in this local expansion is determined by the sign of some point value of the Fourier transform. So if you talk about the vertical segment, then it depends on the value of the sign of the Fourier transform along the phi equals 0 direction, which is the normal direction to this vertical segment. If this Fourier transform value is positive, then you get some negative leading term, which means this cannot be a minimum. Okay, so in the very particular example that I have shown to you, this one, you can explicitly calculate the Fourier transform and show that the omega tilde, the Fourier transform of this profile, is not minimized at phi equals 0, which means the first time you pass this LIC threshold, some Fourier directions becomes negative, and it is not the direction corresponding to vertical segments. That means when you just pass the alpha L in this case, you only allow some tilted segments in your minimizer. You don't allow the vertical ones. So if you only allow tilted ones, it's very naturally expected that it has to have like some zigzag formation. And if you look at this picture, this direction is indeed the first direction for which the Fourier transform becomes negative. And you see that all those zigzags follow exactly this direction of the symmetric one. Okay, so that's all what we have done up to now. And we can see that this framework can be easily generated to higher dimensions. For example, all those kind of calculation about the ellipses, you're just doing some one-dimensional projection and assemble everything together. You can do that basically in any dimension. And we have ongoing work in 3 dimensions, which everything just work very well. And another thing is logarithmic potential. We mentioned that it can be derived as a limit s goes to 0 plus. Actually, this limit is like you can do this limit on any level. Like you can do that on the level of the potential or on the level of the minimizer. And you can recover everything about the minimizer for the logarithmic potential, starting by taking a limit through s goes to 0 plus. So in particular, this means that our result generalizes the previous result on the logarithmic potentials. And another interesting aspect of the minimizer of the ellipse-shaped distribution is that it is closed under the associated Wasserstein 2 gradient close. So although we don't know the well closeness in general for those gradient flows, we do know a particular family of solutions to it, and we can also have long-time convergence of this kind of particular solutions to the gradient flows. Finally, let me leave you an open question, which is when your omega has 2 preferred directions. This one preferred both the horizontal and the vertical, and you see that the numerical simulation somehow gives you some local minimizer which has a fractal structure. And up to now, we are still trying to understand what's going on in this case. Okay, thank you.
Thank you very much for the nice talk. In your talk, you always had this interaction potential consisting as a product of somehow some function depending on the distance and the angle.
Yes.
Is this kind of factorization important, or can you is anything going wrong if you take general function of these 2 parameters?
I think up to now, we only know how to deal with the potentials which can be factorized in this way. So somehow this makes the structure of the Fourier transform very clean. So we can utilize the IRIC property in a very nice way. Otherwise, if the Fourier transform is not well understood, then up to now nothing.
So you mentioned that the LIC is a strict convexity, and then but at the level of the Fourier, it was a non-strict inequality. Can you quantify like LIC convexity? Like, is there a notion of lambda LIC convexity?
Yeah, so to quantify that, basically what I need to quantify is that if you take some compactly supported probability measure and take the Fourier transform, it is analytic in the C variable. So it cannot vanish in any open space. So if you can quantify that, yeah. So I think it is possible to quantify that, but it may depend on the size of the support of your original probability measure rho, and those support size already has an estimate. So I think to quantify that is possible, although this estimate may be like even like worse than any algebraic rate, something like that.
I have a quick question about your alpha star. Is it known to be a sharp interface?
We know that it is a sharp interface just by comparison again. If you have some value of alpha which already collapsed into vertical, then after that it has to be vertical all the time. And whether it is closed or open interval, just to do some kind of weak convergence arguments, we can see that. So we know that there has to exist a sharp interface alpha star, and we have estimate on this alpha star, but we don't know what exact value it is.
See whether there's any questions online. If you have questions, you can just unmute and speak up. I don't see any questions online. Okay, then if no questions, let's thank Sharon again. We'll have peaks after this, and we resume at 14:15. 27 minutes. The tape is back in institute.